Morning, everyone. Is this thing on? Yes? No? No? How about now? Now? It doesn't feel on. Okay. Lights on. Can you hear me in the back? Yes? All right, thank you. Okay, so we're going to be writing a bunch of code today to implement our k-nearest neighbor classifier. Before that, I have a ton of announcements. So Project 3 released today. You are going to be given song lyrics. Data aren't only numbers. And you are going to use those lyrics to classify whether the song is hip-hop or country. Now, you can, in your mind, imagine which lyrics might help you make this decision. However, many of those lyrics we were unable to include for reasons of politeness. This makes the problem harder. The two genres just came closer together, but I hope you'll have fun. Deadlines. So what we've done is, just so that you don't leave it all for the Thanksgiving break where there are no office hours, we're going to get you to do a big chunk of it before you leave, and then hopefully finish up over the break. Checkpoints and deadlines are Tuesday as usual. There is a homework that we will assign on Friday, and we thought about the due date for that. And the early submission will be Wednesday as usual, 1 week from then. But then I had a really hard time, as did my GSIs, imagining our class leaving the Thanksgiving table to go turn in their homework on Thursday at 7 o'clock. And therefore, the regular submission deadline is Monday after the break. And so you can do your work whenever you want. Obviously, you can submit it before that, but really during the break, you do not have to submit anything. What else? All right. We had a change in office hours rooms for Mondays and Wednesdays from now on. Same time, 2 to 5. So Mondays are in one room in Echeverry. Wednesdays are the next room in Echeverry. And other days, there is no change. Basically, we had 3 BIDS days, and 2 of them are now going to be in Echeverry so that the people at BIDS can get some work done. Apparently, the class shows up and is very active, and I love that. So rather than keep asking you to be silent, we've just picked a different room. Are there any administrative questions? We have, short weeks coming up. Anybody, anything, something you don't understand about schedule? All right, so our topic is classification, and this is just a brief review from last time. We have a response variable which is categorical, and we are going to stick to just 2 categories, known as binary response, and we're going to label the categories 0 and 1. Basically, it's yes or no, or however you want to assign your labels, but just 2 categories. And we are going to have an individual who has a bunch of attributes. And based on those attributes, we are going to try and automate a procedure for classification, either a 0 or a 1. And in order to do this, we have to first start with some individuals whose classes we know. And so this is called an initial training data set. And we are going to use it to do our classification. And as we discussed last time, the method of classification that we are going to use, and there are many different methods. We are going to use the simplest one, which is called k-nearest neighbor classification. And what that does is you take your individual, they have an unknown class. You find in your training data the k closest ones. For this, you have to define what close means, which we're going to do. But you find the k closest ones. And imagine k to be odd, because we're going to take a majority vote. So if k is 7, you find the 7 closest people. Each of those 7 people are in your training set, because that's where you chose them from. So you know the class for each of them. So among those 7, there's a bunch of zeros and a bunch of ones. One of them has to be the majority, because you can't have equal, it's odd. That majority class is what you assign to your new person. That's the program. And our goal today is to execute the program. Questions thus far? Anything from last time that we should talk about? Okay, so we had discussed last time that, obviously you can take your entire training data set and build a classifier based on it. But then when you try to assess the accuracy of the classifier, you have a little issue of bias. You have used those data to generate your classifier, and now to test, you need some other data. So either you can wait until you have more data of the same kind, or at the beginning, you can split your original training set into 2 randomly. Use one to explore the heck out of, right? Do your worst with that, build a classifier based on that, and then use the remaining set to do your testing. And that reduces the bias in your test. So I hope today to be able to develop the code with you that will implement the classifier and also do the accuracy. If not, we might have a little bit left over on Friday. Questions? Okay, so what I would like to do is point out, so we're going to build our classifier in little bits, and let me do some basics here. And I'll remind you of a table of data that we had. So we had 158 patients, and the issue was, do they have chronic kidney disease or not? So this was the class 1 represented, yes, they have chronic kidney disease, and 0 represented they didn't. We had binary classification, and we had a ton of variables. Now, what we need to do with data like this is find who is close to whom. Yep, that's one big thing that we have to do. Now, one particular individual is represented by what on this table? By a row. So now, look, we have to look very hard at rows. We haven't looked at rows before. We have looked at variables. We have looked at columns. But now we have to look at rows. And we have to work with rows. So we have to understand rows. And so the first thing I'm going to do is do a little summary of what rows are. Right, so rows of tables. Each row represents one individual. You know that. Do you remember how to extract the data in a column? What do you do? Table.column, yes, and then index. Or a label, yeah? Now, a row does not have a label, but a row has an index, row 0, 1, 2, 3, 4, etc. So does that look like a reasonable thing to do, to extract row number I? Yes? Instead of column, just type in row. And then how about that for picking off item index J off row I? Does that seem reasonable? Yep. So far, it's just like working with columns. But I want you to look at the table here and talk to your neighbor and tell me what is a massive difference between a row and a column. That is going to be computationally very important. Right, what's the difference? The row has different types of data, whereas the column always has the same type of data. Therefore, the column is a what? An array. An array, by definition, must have all elements of the same type. The row typically is not. So it is a collection of elements, but it is not an array. So to go back to our summary, A row is a row object. It's its own kind of thing. And what is its own kind of thing? Shall we look at row 0? So that's this thing here, 48, 70, 1.05, etc., etc., etc. And if you just ask for row 0, here's what you get. It's a row. It is its own kind of object. And notice that you're getting the data in it, but you're also getting it labeled by column. So it's not one of the usual standard Python objects. It's its own little object. And you can't convert this to an array because, after all, this has multiple different types in it. However, you know that you're going to want to work with the numbers. Yes, you have to find distances. You're going to want to work with the numbers. So let's just for proof of concept, item number 1 of this should be what? Okay, so let's say it's 70 should appear there somewhere. Yep. And what you get is just the value. You can work with this. And the value could have a different type. So item number 8, not present, is right here, bacteria. Okay? But what we're going to want to do is work with some of the numbers, and I'll remind you we had a shortened version of this table. We just had hemoglobin and glucose, and we had converted them to standard units just for comparability because we were going to look at pictures. And we had drawn the scatter diagram and noted that the non-kidney disease people were here and the kidney disease people were all the way scattered all over the place. And now we have this new point called Alice, and we want to find Alice's nearest neighbors on that graph. Therefore, we will want the distance between Alice and any one of these points. Agreed? And so that means that when we look here, Alice is the point, I just set it to be the point 0 here and 1.1. So Alice is an array. You agree? So the other points now are in this mess. So a natural thing to do is to just extract the numerical bits. How about that? Leave out the class and color information. Just take the information that you want. And now look at the rows of this. Aren't they all numbers? So it would be really nice if you could convert these rows to an array, because then we're just in business. We know how to work. And happily, numpy.array does exactly that. So if I take row 3 of this, it's 0, 1, 2, 3. I should get 0.59 and minus 0.19. That's a row object. But now if I take that row and apply np.array, please note, not make array. Numpy.array applied to that gives me a very nice little array. And it's just it's an array of the usual kind that we know how to work with. Right? So the moral of this story is, if you have a row object that contains all elements of the same type, apply np.array to that to get an array back. Do not apply make array. Make array does not operate on rows. So far, so good? So the one thing that you have to remember is to use np.array here and not make array. Yes? Well, let's do it. That's what you're asking for? Oh, no, wait a minute. I changed what CKD was. Sorry. No. This is my own. I should not do this. All right. We'll read the thing again. We'll run this again. And now we'll run this. Okay. That is a mess. Right? It is a mess. Do not use it. Right? It's great that we have the, so now I have to run this thing again. Okay. It's great that we have the, we should be testing stuff out. but you can't work with that object. So in general, in any statistics or data science, when you're working with something, it is a great idea to reduce your data set to just what you need. You are much less likely to get messed up. All right, so so np.array gives me rows, and now Alice is the array 0, 1.1. Patient number 3 is this other array, and we want the distance between those 2 points. High school geometry graphs, the distance between 2 points is something that we need to find, and I am going to skip through this here. All right, I've got 2 attributes, x and y, and I have 2 points. Yes? So the first point is x0, y0, and the second point is x1, y1. You imagine 2 points on a graph? The distance between them. Does that look familiar? So you have 2 points, and you can think of those as the hypotenuse of a right triangle, right? And then you have the one leg is the difference between the x coordinates, the other leg is the difference between the y coordinates, and this is the result of whose theorem? Pythagoras, the most famous Greek mathematician of them all. Yep. And what the lovely thing is that this is something we can visualize in 2 dimensions. The wonderful thing is that if you're in 3 dimensions, there is a natural extension. You don't have to worry about it. It just works. And some of you will have seen that geometry and some of you won't, but it's an easy thing to accept. And if you have 17 dimensions, then what do you think is going to happen? You're going to have 17 terms like that. Yeah, you take the x's and the y's, you subtract them, and then you run this Pythagoras thing on all of them together. And that's a wonderful thing that helps us calculate distance between 2 points. Please, the one thing to remember is that all the x's, y's, z's, w's, they're all numbers. Right? If they're good and bad, then none of this makes any sense. Okay. So for the distance between Alice and this point, what do I have to do? I have to subtract a coordinate by coordinate. Since Alice and my point is now an array, when I do the subtraction, what do I get actually? Why are we doing this? Okay. We subtract Alice minus, who's my patient? Yes? And so now I square these guys. I have an array of squares. Now I add these, and I am being very particular, reminding you array, 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 because we now have different types floating about. So I add all of those. I have that, and that's wonderful, but it's on the wrong scale entirely. And so I will take a square root, and we have the distance between those 2 points. So I'm going to pause for a second, and I want you to take a look at that line and ask me any questions about the calculation of distance. I did np dot square root, and I could have done raised to the power 0.5. It's just I like to read a piece of code. It's the square root of the sum of the da-da-da-da-da. It's just for me, right? Because in the end, I'm taking the square root of a number. So I could just have raised it to the power 0.5. You're absolutely right. Yes? Yes. I used patient 3 just because that was the patient whose row we picked off. We just picked off this person. Yeah, just because I felt like it. Right? So we could pick off patient 5 and we'd get a different distance. So that's important to note that Alice is fixed. Alice is the red point. And the patients are all of these points. I've just picked one of them and found the distance. You know that if you can do that, then you can find the distance for all of them. Yep? Okay, now you would love to be able to find the distance for all of those patients at one go. Yep? For this, isn't it a great idea to have some functions written? So when we write some functions, we are going to write this distance function. Does that seem like a good function to write? Okay, when you look at that, please tell me. I haven't, been a good programmer and written documentation for it. Could you please look at that and tell me point 1 and point 2 are what exactly? In your head, what should you be seeing? You should be seeing arrays first, because I'm subtracting them and doing all of this stuff. Yep. And each array, if I just look at point 1, what does it have in it? X and Y coordinates for point 1. Now, I'm just going to take you one step further. Supposing we were in 3D. What would point 1 have? The X, Y, and Z coordinates, would the code change for the distance? No, because the subtraction, the arrays can be subtracted regardless of how many dimensions you have, right? So what we're doing now is we can visualize everything in 2D, but the precise same code you can work in 17D. Nothing needs to change. All right. So that's a distance function between 2 points whose coordinates are in arrays, but what we're going to want to do is, Alice is fixed. We're going to want to find her distance, the distance between this point and any point here. And aren't these points in rows of this table? So what we're going to do is define a function called distance from Alice and input a row. So who's Alice? Alice is our fixed point. Alice is 0, 1.1, the array. And we are going to find the distance from Alice. We're going to feed the function a row, and it's going to calculate distance by using our distance function. So distance between Alice and what is this? What happened there? What did we feed it? We fed it a row object. Yes? Now, we have taken care to make sure that that row object consists only of numbers. Otherwise, distance doesn't make sense. And now we convert that to an array. Why do we have to convert that to an array? Because the function distance takes 2 arrays. All okay? All right, so we've got distance from Alice, which is a function that we have defined, and what we are going to do is we are going to find distance from Alice of row number 3. Why are we going to take row number 3? Because I picked patient number 3 just because I felt like it. We need to see that our function works. So what is the answer that I should get if I run distance from Alice of this table row 3? Can you see it on the screen? What's the answer that I should get? 1.421 whatever blah blah. Agreed? This is the answer I should get, because this is the distance between Alice and that particular patient. All right, here's the moment of truth. Well, that's good. Correct function. So now what we have is a function. Alice is a fixed point. What we have is a function. We feed it any row. It will give us the distance between Alice and that row. We'd really like a one-liner that applies this to the whole table, right? We don't want to write a for loop, if possible. We could, of course, for every row of the table, apply this thing. However, apply, do you remember how to use apply? Table.apply, name of function, and the column on which it applied. Yes? Those were functions that applied on single numbers, on single values, right? Not could be categories, but on single elements. There is a lovely thing. Apply has a lovely property. Look at this last property there. If you use apply without naming the column, it just passes the whole row to the function. It passes all the columns to the function. You didn't specify the column, so it says, I will take them all. Right? So if in a row you take all of the columns, then you're passing it the entire row. And what is the advantage of this for us now? We have a function. We wrote a function, distance from Alice. What does it take as input? A row. Yes? So we can plug that in to table.apply. Apply will feed it a row. It'll spit back the distance. And it will do it for every single row. To see how that works, I have just taken a very short set of Supposing that was our entire training set, 4 people. Yep. If I apply to this table the function distance from Alice, what do you expect to get? First, what type of thing are you going to get? You're going to get an array. Apply spits back an array. And it is going to apply the function distance from Alice to each of these rows. So you should get 4 distances. And that is what we get. Is there a number there that you recognize? One of those 4. Anybody recognize? Which one? The last one. It's exactly the same as what we computed. Yes? So this is a good thing. You can compute from any fixed point the distances from your entire table. Yep. So what we're now going to do is we're going to find the distance between Alice and our entire table, not just these 4. To do that, we are going to take our function, which is chronic kidney disease. We're going to append a column, and we're going to call the column distance from Alice. Okay, now look at what I'm doing here. To what table am I applying my function? I am applying my function to this table, not the original table. Because, why? Because the original table has a bunch of junk in it that doesn't help me calculate the distance. Yes? The attributes are purely hemoglobin and glucose. So when you compute distances, they must be based on the attributes only, otherwise you'll have a mess. All right, so where was I? Okay, so on the attributes table, we are going to apply the function distance from Alice, and we are going to take a look at what we get. This is going to be an array of distances, and we get something that looks like that, and it has 158 distances that we have just computed. All right, what was the point of computing these distances? What is the end goal? Find her k nearest neighbors. Yes? What do I do to this table to spot who her k nearest neighbors are? Sort. Yes. There you go. And so if you want her nearest neighbor, that's right here, her 3 nearest neighbors, 5 nearest neighbors, the whole lot. Yes? So if I want her 5 nearest neighbors extracted from this, what do? I take. Yes, exactly. There you go. Those are her 5 nearest neighbors. And essentially, you're on your way. You've got your classifier here. Right? Because now what are you going to do? What are you going to look at? Which column of these? You're going to look at class. And you're going to look at how many 1s and how many 0s you have. How many 1s do you have? 3. How many 0s do you have? 2. 1 wins. So you're going to go classify Alice as 1 of the blue points. Shall we see where these points are on the graph? Why don't we see where these points are on the graph? Everyone clear that there are 3 blue points and 2 yellow points that the classifier thinks are the closest? Okay. That's Alice. And that one is the closest point. That one's the next closest. And these are the 3 blue, and here are the 2 gold. Okay. I'm going to pause for a second, and I am going to scroll back to this code here, calculating the distance table. And I would like you to stare at it, talk to your neighbor, and sort out, are there questions? Because obviously what you can see is that something we can do for Alice, we can do for the generic new point. Right? So it's important to understand what we've done for Alice. Then the generic new point will become easier. Okay, let me ask some spot questions here. This thing, what is that? Distance from Alice, what is it? It's the name of a function, yes? That function takes what as its argument? A row as its argument. How is that coming into this code? Apply without a column label gets fed a row. And then it does that to all of the row. It returns an array, and so you're in business. Okay. So what I would like to do now is we've done 2D examples so that you have a very good visual sense of what is going on. But usually you're going to want to use, 5, 7, 5, 10, 18, lots of different attributes. And what I'd like to show you is that 2 attributes do tell you something, but sometimes having more than 2 can be extremely revealing. And we'll do this. This is an example. The examples are mainly from David Wagner. So this is banknote data, and let me tell you about these banknotes. There were 1,372 banknotes. And the issue, you are not going to understand what the variables are, just listen to the story. A bunch of banknotes, and the issue was to decide whether they are fraudulent or not by taking a picture of the note on your iPhone or some kind of little camera. From that picture, can you tell whether the banknote is fraudulent or not? And people who know about such things developed various variables for these 1,372 banknotes, which are variance, skewness, kurtosis, etc., etc., and each one was classified as 0 or 1. Yep. And the idea is, if we have these data, is there any way we are going to be able to take a new banknote, take a photo of it, and say, is it fraudulent or not? That was the goal. So we have some old banknotes that we know whether they were fraudulent or not, and we know their numbers. And so, okay, so how do you decide this? You start plotting, yeah? Because you have no idea what these variables look like. You start plotting. So I give them colors, and okay. So here are 2 of the variables, variance and kurtosis, and, well, they're kind of separated. But you can see a bit of an overlap, yep? So you should be able to classify, maybe not with tremendous accuracy, but there's something going on there. So how about another pair of variables? These are the blue and gold dolphins, right? And you can see there are patterns, and there are patterns that you would not expect and not necessarily known by theory. But there are patterns. Again, here you see you ought to be able to classify, but then there is this place where the 2 dolphins overlap, and you don't know who's in the foreground and who's in the background, you'll have trouble there. So by looking at the 2 variables, it looks like you have a good shot. However, you can do a 3D plot of 3 variables. And when you do that for 3 of the variables, so skewness, variance, and kurtosis, you ready for this? You can just tell them apart. You put all the variables together, suddenly you've got a classifier. So this kind of thing is very difficult to predict ahead of time, right? And that is why you just have to mess with your data, your training set, and try to recognize different aspects to use. And that is why you want to be able to have a program that takes more than 2 attributes for things like this. So as you know, our distance function, yes, was that a question? Yeah. You can tilt it around and play around with it. I won't do it right now because I can't do it in real time. But you have to get the point of viewing can change, and you can tilt it around. Indeed, you can. In another iteration of this course, I'm hoping for the spring. A lot of this stuff that I show you by changing values of variables, like change R, what happens to the scatter, I'm hoping we'll have the time to actually make sliders so that you can move the slider and see. We just haven't had the time, sorry. How many dimensions will this thing plot? Yeah. Well, you can only really see plots in 3D. We can't see 4D, right? So any number of dimensions that you give it, it is going to reduce it to 3D. So with 4D and up, we're kind of stuck. And here is where imagination really takes a beating. And this is why we have courses in multidimensional arrays, and they are called courses in linear algebra, Math 54. Yeah, this is what they do, because you need to understand stuff that you can't draw pictures of. All right. So what we're going to do now is we are going to apply what we have learned to make a general classifier. And the banknotes are lovely. I'm a bit sick of diseases. I like wine, so I have data on wine. These are 178 Italian wines. And you have the chemical composition, various chemicals here. That was their spelling. I would use a K, never mind. And there are classes, and the classes, the wine is of class 1 or class 0. The classes are the type of grape, the specific variety of grape known as a cultivar. And what you'd love to be able to do is to see whether, given these measurements, can you say whether a wine is of type 1 or type 0? That's the goal. Now, before you attempt something like that, it would be a great idea to actually see whether you think that's even reasonably feasible. So I started messing around. I drink wine. I don't actually work with wine, so I had to do something with these data. And so I just tried drawing some pictures. The blue ones are type 1. The gold ones are type 0. Looking at that picture, do you think will we get a classifier? Yeah, kind of. There's one gold point in there among the blue, but that does look like there's some separation. Yep. And there's, if I draw another pair, I didn't do triples with this one. Kind of, again, the blue points are in one place, the gold points are another. There's a little bit of overlap. It's not always true that they're separated like this, but it looks like we should be able to get some kind of classifier. All right, so the first thing I'm going to do is I am going to pick off the attributes. And we want to be really clear. When you classify, this class column is wonderful because this is what you're going to test your accuracy against, right? And you are going to also use it to do the final classification. But the distances are based only on the attributes. So the first step in any classification is just to extract the attributes. And I chose a data set where the attributes are all numerical. So I don't have to drop anything else. Okay, so here are the attributes, and what I'm going to do is I am going to look at this row and this row, which are of the same class, and apply our distance function to those two rows. Can you please look at that line of code? You see that we've picked off the first two rows of the table? Yep. We have converted them to arrays. Why? Because the distance function takes arrays. We are able to convert them to arrays. Why? Because the rows are all numbers. Yep. And then we run distance, and I get a distance, and I have 31, and I have no idea. Is that a big distance? Is that a small distance? I have no idea. What I'd love to do is compare with, if I just take a row number 100, that's in a different class. Yep. So if I take the distance between something in class 1 and class 1, that's something. If I take the distance between something in class 1 and class 0, do you expect that to be bigger or smaller? Kind of. If their classes are separated, maybe bigger. Let's just take a look. So why don't I just stick in 100 here? Aha, bigger. So it looks like this distance function is picking something up. And remember, the distance function is using all however many variables there were, not just two. It's picking something up. And so now we are going to put together our classifier. And look at that. Look at that. The interesting thing is we've done it all, right? We're just now putting it together. So please note the top one. Distance is the exact same distance function that we defined before. I'm just putting it there so that we remember what it is. Just focus on the distance function, please. We good? All right. What I'd like to do is I would like to skip the all distance functions for now and go right to the end. What we're going to do is we're going to find our k closest points. For that, we are going to need a table with distances. First line. You agree? We need a table with distances. We sort that table by distance, and we take the top k. Do you remember doing that? So what I'm asking you to do is I'm asking you to look at this last set here. We construct a table with distances. We sort that table by distance. We take the top k. That gives us the k smallest distances. Yes? Between what and what? Between Alice, right? You've got this point that you're trying to classify. Between that and everybody in the training set. Right? So you've got your new wine and you've got all of the other wines in the training set, and you want to find, say, the 5 closest. Right? Okay, so that's what you have to do. In order to do that, you need the table with the distances. Table with distances just says, supposing I have all the distances, I will just append a column. So what I'd like you to do is go up now, read table with distances. What is that doing? It's operating on what? Your training table. Yes? And it's doing what to the training table? It is sticking another column on it. What is that column called? Distances. What does the column contain? Well, allegedly, a bunch of distances. We'll see about that. Right? So at that point, your table has all your training data and, all, in particular, all the classes as well. Yes? It has all the distances, and so now you can find the k closest. So the whole deal is to find all the distances. Yes? Remember that we created a function called distance from Alice, and we applied that to our table. Now we have some random point, right? So we have exactly the same function, distance from point. Calculate the distance between the new point and a generic row. And then you apply that to the entire table. What's the new point? It's the point that you got in your distance function, in your original function. So take a look at that. There's a few steps in that, but I want to, actually let me pause for a second. This one should be clear. We're good with this, the distance function? All right, I would like to make sure that you're good with closest. Questions about closest, ask now. We're going to give it a training table, we're going to give it a new point, and we're going to give it a k. Just assume k is 5. We're going to do 5 nearest neighbors. Yes? It's going to work with this table of distances, and it's going to find the 5 closest. Is it clear how it's doing that? Yep? Yes, no, or maybe. That's okay. What about this? Creating the table with distances. What's happening here? It's just a width column. So what's the hard thing about this part? It's this. How did we get the distances? So when you look at this entire screen full of code, the thing that matters is the all distances function. So what does all distances take? It takes what you wanted to take, which is your training set and the coordinates of your new point. And it is supposed to return to you an array of the distances between your fixed new point and all of the points in your training set. Yes? Yes? New point is, well, it could be a row. You notice that I'm converting it into an array, so you could just imagine it as a row. Okay, so I will pause and take questions. Why did I do this? The red stuff is all a comment, right? There's no code happening. The first thing I do is I take the training data set and I drop class. Why do I do that? Why did I drop the class? Because why? It's not an attribute, it's a category. I need to calculate distances. I only need the attributes, right? Step 1, any classifier, you will be dropping the class. Okay, now what? We're going to find distances based on the attributes table. Okay. So to the attributes table, you're going to apply a distance function for every row. And that distance function calculates the distance between the row and what? You've got a row, and what's her name? Alice. Right? Who's Alice here? Alice is this person. And that is why we had to define this function, distance from our new point, which previously was called distance from Alice. So every time the function is run, this thing, new point, is exactly the same. It's Alice over and over and over again. It's just the other one changes. You do it one row at a time. So I'm going to do this definition, and we are going to take our favorite wine, which is the very first one on this table, and we are going to find the distance between it and every row of this table, right? One of those distances we already know. Which one do we already know? With itself, what's the distance? 0. That's kind of a check of whether our function is working. Yep, and the others we don't know. It's going to come out due to some calculation. So what we are going to do is we are going to define the special wine to be the row 0 of my attributes table. Yes? And we are going to apply our function closest. The training data set is this whole thing. Yep. And we're going to say that's our training data set. Find the distance between every row of that and our special wine, and give me the 3 smallest ones. We've been saying 5 thus far, but K was generic, so we're just going to do 3. Right? Please note that we're feeding it the training data set wine, which has the class column. That's why our function had to drop the class column first. Yes? Okay, you ready to run this? The 3 closest to the top wine are these 3, whatever they happen to be. Recognize this guy? This was the top wine. What are the distances? 0, followed by 10, followed by 22. These are the 3 smallest distances. And these 3 have what class? All of them are class 1. So how are you going to classify wine number, that special wine? You're going to say it's a 1. Was it a 1? It actually was a 1. Now, this is cheating. Why is it cheating? Because it's in there, in the classifier. But never, let's cheat for a while. Right? We will stop cheating on Friday. Right now, we're going to cheat. Okay. So in order to figure out what is going on here, we have our closest data set. We need to define what the majority is. Yes? You want to look at this? What's going on here? If I feed it these 3, the top K classes, I'll be feeding it 1, 1, 1. Yes? This function majority counts the number of 1s. How much is it going to get? 3. Then it counts the number of 0s. How much is it going to get? 0. What is it going to return? It is going to return 1, because the number of 1s is greater than the number of 0s. Yep. And then we are just going to run that and get a class back. Your classification, the thing that we did by I, there were 3 1s, and we said the majority is 1. That is now done automatically. So you have a classifier. The business for the first half of Friday is checking how good it is. Okay? And then we will move to something else.